You should have just gone me then.
Alright, let's get started on the lecture for today. So we're almost at the end of the semester. We have 3 more program analysis topics, and then Steven's going to do his power lecture, but not much more now. Today we're going to be focusing on another dynamic analysis technique. Last week we finished up fuzzing, which was another one that was very automated. The techniques we're going to talk about today are a little less automated. You got to do a lot more setup, but they're still potentially very useful sometimes. Yeah, in terms of assignments, project 5 was assigned last week and is due May 4th. This project includes another heap challenge and 2 fuzzing challenges. The presentation checkpoint 2 will be released today, and it will be due in about 2 weeks. The exact due date will be on Gradescope. For this one, we're asking you to basically tell us what you've been doing since the last checkpoint. What have you accomplished since? What have you been focusing on? What did you learn through your reverse engineering? Did you find some bugs? And so on. You're also going to talk about, this doesn't have to be finished yet, but since your final presentation does need to include what you did using some form of automated program analysis, this checkpoint should include what kind of program analysis you chose to do. And you're going to talk a bit about what you have planned with that, maybe what you've done with it so far. Maybe you should start doing some setup if you want to fuzz it. Maybe you recompiled it to include coverage instrumentation. Maybe you've even done some fuzzing. Maybe you've decided to do some form of static analysis using LLVM or whatever. We're going to talk about that next lecture more. Or what we're going to talk about today. There are different things you can do, but kind of for that checkpoint, you talk about what you want to do and what you've chosen to do there. And a small homework on program analysis is going to be released today afternoon as well. Any questions on the course right now? Or questions on like project, last lecture? Okay. Okay, so today we're going to talk about Intel Pin. We talked a bit about its use cases, some other dynamic binary instrumentation frameworks. We're going to talk about JIT compilers. We'll do some examples and demos. If we have time, we'll talk about some deobfuscation, although we haven't had the malware lecture yet, so we might leave that out. We'll see. And we'll talk a bit about dynamic taint analysis and various design consideration and how to actually do it in practice a little bit as well. So starting with Intel Pin, this is a tool that, as the name suggests, was developed by Intel. It is a dynamic binary instrumentation framework. So what this means is that it's number one, a dynamic technique. So it is run by executing the program. And it is a binary instrumentation technique, so it doesn't operate on source code. It operates on the provided binaries. So it works against compiled code. You don't need source code, and it actually runs the code. So our requirements to use it are pretty much you need to be able to run the code. But you don't need source code. So what this tool does is basically that it enables you to write modules that execute some program, and you can basically insert code at arbitrary locations in this program. This is done via various hooks. So let's say you have this is your program, you have like your control flow graph. You could, using pin, say, you don't need source or anything for this. You just have your program, and you can tell pin, at the start of every single block, insert a print instruction. Just like printf, hi. And then at every single block, it's going to execute this print and print that out. You could do the same at every single function, print that out. Or you could say at every single instruction, insert another instruction. So assuming like this might be a list of instructions. This could be an add, move, XOR, whatever, some instructions. And you can tell pin to, after every single instruction, insert a call to like some form of function you use to measure something. So this could be measure how many add instructions are executed. So you could, after every single add instruction, insert a instruction that increments some counter. So this can be very powerful. You have some program, and you can just instrument in arbitrary ways without having to modify the source code, without even having to have the source code. So you could take some binary in your system, for example, ls, and just use pin to count the total number of instructions that are being executed during runtime of ls, or do some much more complicated analysis as well. Yeah. So one thing though is that unlike tools like LLVM, Pin is not meant to be an analysis framework. It is more of an instrumentation framework. So what this means is that you usually use it to collect some data, not to analyze it. So you would run it against some program and have Pin emit some data for you. For example, how many times something has been called. Or it could, for example, even give you like an array for every single instruction, how often every single instruction has been called. Inside of Pin, you wouldn't necessarily analyze it. You would use Pin, write that out to some log file, and then maybe use some different tool or start script it out yourself to like do the actual analysis on it. Because Pin's APIs are mostly focused on just collecting the data, not on terms of like actually analyzing this data. So yeah, like some simple analysis you can do at runtime, but in general, if you do want to do like some more complex analysis, you do want a different tool for that. In Project 6, so this is not going to be released for a while, but for that you'll be combining Pin's instrumentation in combination with Ghidra's scripting ability, where you will take some binary, run it using Pin, measure something in that binary, and then you're going to use that to script it out using Ghidra's analysis and basically make your reverse engineering life through that easier. I can just quickly say what the challenge is going to be in that case. So for this project, you're going to use Pin to basically, you know, like when you have a program, there are indirect calls. So you could have, for example, the normal calls, which just like, say you could jump to some function, which would usually be a call instruction, I guess, but whatever. So you could jump to a function. There's also different constructs where you might instead jump to a register. So when you're reverse engineering with Ghidra, when you have something like this, jump racks, or like jump to some memory location, you might not know where that actually jumps to. Like what function does racks point to at this point? When you're just doing static analysis using Ghidra, it might not know that. You might not have the ability to know that. It could also be C++ with this virtual dispatching where something like this is very useful. So what you're going to do for this project is use Pin. You're going to run some binary, and you're going to find every single one of these instructions that jump to some non-predefined location, so non-constant location. And using Pin, you're going to print out where it actually jumps to. So you're going to hook every single instruction. You're going to check is this a jump instruction? If so, you're going to check during program runtime where it's actually jumping to. And then you're going to emit that pair of where this instruction was and where it calls to. You're going to emit all those to a log file. And then using Ghidra, you're going to script it out that for every single one of those that you found, it's going to resolve the call in. So you actually, during your decompiler window, you can then see to what kind of function those indirect calls actually went to. So you can see when you're doing reverse engineering, or especially when you're doing some like malware analysis where you deal with some very heavily obfuscated code, where, for example, every single one of your function calls might be a call like this. And then Ghidra is not going to be able to generate you good control flow graphs at all. You're not going to know what calls what functions. You're not going to be able to have a lot of information about your program. So you combining it with like some form of dynamic analysis, like for example Pin, you can make your life a lot easier. Hope you can see how that can kind of be useful. We'll go over some more examples later. Any questions on it so far? Okay. So we can talk about a couple of other use cases. So in terms of program analysis, first of all, there's various forms of performance profiling. This is, for example, Intel Pin is, for example, used with Intel's VTune profiler. This is an application you can download, I believe it supports Windows and Linux, and you can basically run some form of program under Intel VTune, and it's going to start benchmarking your program. It's going to tell you where you spend most of your time. You can use that to, for example, do performance profiling, and all of this is done using Intel Pin, where it instruments your functions, your instructions, your blocks, whatever, and collects a lot of runtime data on what executes for how long, what executes the slowest. And as a developer, you can then use that to speed up your program, since you can see what exactly are your slow paths. You don't just optimize some random function that you don't know if it's fast or slow, or if it's even like relevant, if it's called a lot. You can use this benchmarking tool that is based on this and get a lot of actual information on what's relevant. There's also memory profiling, so like LogRind does, for example. This is actually based on a tool like Pin, not Pin exactly, but a similar tool. You can do trace collections, so you can hook every single instruction, and for every single instruction, you can print out the address of the instruction. And then when you execute a program, you can print out the entire trace and can see what instructions were called in what order, which can sometimes also be very useful, especially when you're dealing with code that has a lot of these like virtual functions that you can't find out statically where they go to and stuff like that. If you can do it dynamically, you can just print out an entire, like, you can print out which function. For example, you can only print out the functions maybe. It might be a bit more easier to see them. And like for every single function that's being called, you'll print it out. And then you have like a full trace of the program and what's being executed. You can also use it for taint analysis, but this is a topic we're going to ignore for now. We'll get there at the end of the lecture. I don't want to explain that yet. This is also used for when you're studying computer architecture and how your processor behaves at the lowest level. It can be used to, for example, simulate some form of processor or cache simulations. MIT, for example, uses Intel Pin in their PhD computer architecture course. And Intel, for example, uses this internally, at least as far as the public is aware, to model things like branch predictions or cache setups. Because you could, for example, find every single branch and then like see what like implement your prediction algorithm inside of Intel Pin, and then you could see how often your predictions are correct or not. If you're not familiar with what branch predictions are, it's fine. It doesn't really matter for this. You can also use it for binary translation. So let's say you're running on some old processor, some like 20-year-old x86 device maybe, and then you're trying to run a program that maybe has some instructions that didn't exist yet back then. x86 evolves over time. Maybe now there's some instructions that didn't exist 20 years ago. So what if you still really want to run this? You don't have source code for it, or even like the other way around, it's like some really old code that doesn't run on newer systems anymore. Well, using Intel Pin, you can then hook the instructions, find the instruction that doesn't run on your processor, and then just replace it with different instructions that do the same thing. So you can dynamically then get your programs to run using Intel Pin. It's going to run a bit slower because Pin has an overhead. We're going to explain later how exactly it accomplishes all of these amazing things. But yeah, you can see that it's very useful, not just for security, but for general program analysis in general, for pretty much every area. You're doing systems development, you're going to use it for benchmarking, you're going to use it to collect traces maybe for your program. It might be hidden behind other tools that you use, but those types of tools are always kind of used if you've ever used Valgrind, you've used the dynamic binary instrumentation framework that operates very similarly to Pin. And you can use it for internal security for topics like malware deobfuscation. Or when you're hitting a new code base, maybe this code base has a lot of different paths it can take, and you want to see where it starts, where the main functions are, the most relevant loop functions. You could use Pin to generate a function trace of all functions that are called, and you might make your static analysis a lot easier by knowing what to focus on, what's actually being called. We'll talk maybe on how it can be used for malware deobfuscation later a bit, but the essence of that is pretty much there's a lot of code being executed in malware, or a lot of obfuscations that don't just tell you where to jump, for example. So something like this might be very relevant, and also a lot more complex obfuscation techniques that you can just automatically deobfuscate using Pin. Any questions so far? And anyone think maybe of a situation in the past where they maybe programmed something, ran into a bug or some issue, where they think they could have maybe used a tool like Pin to make your life a bit easier there? We've used debuggers a lot for def debugging, for example. Can you think of maybe a time where you might have, if you had known the tool, where you might have been able to use Pin to do it instead? Yeah.
If you have certain instructions that only get called a couple times, and you want to know when exactly they're being called to make sure it's happening at the right time, you could set up a Pin there, print out something that tells you that you're here.
Yeah, exactly. You could do that, for example. So you could do printf debugging, for example, without actually having to insert printfs into your source code. You can just tell Pin to do that for you. Anyone else have an example? Sure.
If you're spending a lot of time in a loop or something, or you get stuck, you could check how long it takes in each part.
Yeah, that for example is a lot of time profiling your code, how often the loop's executed. Maybe you could dynamically print out the loop counter after every single loop iteration, see if maybe something's getting corrupted, whatever. Situations like that, there are a lot of situations where you could be using it. Yeah. No one else has anything? Yeah, okay.
Memory leaks.
Yeah, for that you'd probably just use Valgrind instantly because the tool is very mature at this point, very good. But yeah, it is based on tools like pin, so yeah, that's good too. Okay. Another thing that you probably wouldn't really do it yourself that way, but let's say you get some untrusted binary. The usual approach is you might, if you actually want to run it, you might just run it on a VM, be safer. Another thing you could do is run it under pin and then hook every single syscall instruction and make sure there aren't any syscalls that, for example, delete your your /root directory or whatever. So you could do that, for example, as well in the terms of malware analysis for running untrusted code. You could run them under pin and then hook instructions that can potentially cause damage, like syscalls, and not check them before they actually execute that they're safe. So things like that you can do. You have a lot of control over what's actually happening in your program using pin, and that's really cool, I think. So to quickly talk about a couple of alternative dynamic binary instrumentation frameworks. Starting with Dynamorio, this is the one I wanted to use for this course initially, because in general it's more powerful and it's also generally faster than pin. But kind of when I was playing around with it a bit, it was a big pain to set up in many ways. It is fully open source as well, which pin isn't, which is really nice. But Dynamorio is kind of, it felt like it's more suited if you want to build a bigger analysis framework on top of it. So if you wanted to build the next logline, for example, you probably base it on Dynamorio. Meanwhile, pin is really good for security researchers because it's kind of very easy to set up, very quickly to script out a little thing that does what you want. So I thought that for this class, pin would be a bit more relevant. But if you want to have some idea for some advanced tool you want to write, Dynamorio is probably the better choice. It has existed for probably 20 years at this point. It's very old, but also very powerful. Yeah, it felt a bit less supported as well when I tried getting filed some issues, get some bug fix, didn't really happen, but it is what it is. So we're going to be using pin for this class, but Dynamorio exists as well, and you may want to consider if you want to do something like this. There's also Logrind, which you all know as the memory checker, most likely. But Logrind is actually a full dynamic binary instrumentation framework that you can also use to script stuff out. The tool Logrind is still in use, but the framework itself is basically superseded by Dynamorio at this point. And Dynamorio also has Logrind alternatives based on its own framework that operate just as well or even better in many situations. And in terms of performance, API support, and pretty much everything else, I would say that Logrind is pretty much superseded by Dynamorio at this point. But yeah, it still exists and is kind of the grandfather of all dynamic binary instrumentation frameworks. That's kind of where it all started. So it's worth mentioning, but yeah. There's also Frida. This is a lot less powerful and also slower in general, I would say. It provides the same capabilities where you can hook functions and stuff, but you don't really have the very fine-grained API of where you can insert single instructions and so on. It is a lot simpler to use though. And unlike pin and Dynamorio and stuff, which have C and C++ APIs, Frida has a JavaScript API, which a lot of, especially non-systems developers, will probably enjoy more. It's a tool that's very commonly used if you're dealing with, for example, Android devices or anything where you're dealing with non-C code like Java and so on. You can use Frida to still hook stuff, especially if performance isn't really an issue. So you wouldn't really use Frida to build an entire tool on top of, most likely, but it is still very powerful, and depending on your use case, it can be the correct tool because it's very easy to get set up and get started with. And there's GDB. Not much to say about it as a DBI framework. Its API is very weak for stuff like that. And it's also very slow because if you would want to hook every single instruction, you could do that. You could set a breakpoint at start and then single step and then do something and single step again. You could script that out using GDB's API. But it's very slow and it's not really what you want to do. Questions on this? Let's talk about just-in-time compilation. So why are we going to cover this here? We're going to, I think next slide, I believe, right? Yeah. Starting next slide, we're kind of going to, or even this slide of it, we're going to talk about how pin actually works in the background, how to accomplish all these things. And to understand this, we need to understand at least the basics of JIT compilation. So this is basically a technique that is used by pretty much all interpreted languages that care about performance. To basically make the interpreted code faster. So the Java JVM uses it, pretty much all common browsers use it in their JavaScript interpreter and so on. And the basic idea is that you don't just interpret the code, you actually compile it at runtime. So the nice JavaScript code you write, you would think that it might be kind of like the 220 interpreter you wrote. Maybe it just parses them into some tree, like the abstract syntax tree we talked about in 2 lectures ago, and then it kind of just walks through the tree and executes it. But that's not really what happens in modern day interpreters anymore. They also try to kind of compile it to machine code. This is not done ahead of time like you would with C code, where you have your source code, you compile it, and then you run it. This is done during execution. So you give it your JavaScript source code, and while it starts executing it, and while it's executing it, in the background it's going to start compiling it to machine code, and then run that instead. So we can talk quickly about how like the most popular target suite, like the Java JVM, for example. So when you give it your Java code, this is going to, using Java, you always go down to bytecode first of all. So you have your, erase that a bit. So Java, JavaScript, even some Python interpreters, although the main one doesn't do it, you have your source code. This source code, the first thing it does is going to compile it to bytecode. So this is not actually assembly, but something that looks a bit like assembly, but has a lot more information encoded in it, and this can then be emulated. So let's say you have something like in your source code, if you have like a is equal to b plus 3, the bytecode for that could be looking very similar to assembly, where it could basically be the exact same thing. But then instead of having like an instruction like an x86 instruction emitted for it, like add rax R1, R2 or whatever, you're not going to have an assembly instruction like that. You're instead going to have this instruction. And inside of the emulator, you're going to have like a large switch statement or something of that sort that checks, okay, what instruction is it? Okay, it's an add instruction. And it's going to give it to the some add handler, and this add handler is then going to handle the add instruction, and then instead of using registers directly like x86, like machine code would do, you're going to store your variables in some memory location, and so on. So you can see how this is kind of like assembly, but you're actually emulating the code instead of just running it on your CPU, and this is going to be a lot slower. For every instruction, you need to manually decode what the instruction is, you need to manually decode the arguments, you need to do the operation yourself, and like store them into memory. You don't have like the optimized register allocator and all that stuff that goes on with like a proper compiled code. But it's still faster than just like having a tree walk interpreter, as like the 220 project had. So from this bytecode, what you can do at this point is either you just execute it, which is the basic step. So if you, for example, use Python and use the default interpreter, this is kind of where Python stops. It's going to do some optimizations to make the bytecode a little bit faster maybe, but in general it's going to take the bytecode and execute it. There are some other Python interpreters like PyPy, I believe, that have JIT compilation, but the default one doesn't. But then if you look at Java and browsers used for JavaScript, they go one step further, and that's where kind of the JIT compiler comes in. So they don't usually do that for all of your code, but let's say you're executing your bytecode, and then you see that you have function f, and this function inside of this code is called in like a loop, and it's been called like 10,000 times now. So this function is very popular, it's executed a lot, and you're slowing down your program a good bit since you're always executing it from this bytecode. So every single time you execute it, you need to reparse all the bytecode, redo the switch case, all the operations, and this is kind of slow, especially something that's called this often. So what it can do then is that it's going to take this function and just compile it to machine code. So it's going to send this one function to the JIT compiler, and this JIT compiler is going to just compile this function to straight up x86 assembly. And then during the execution of your code, the bytecode interpreter is going to then call into your assembly, and once this function is done, it's going to call back into the bytecode interpreter, and so on. How exactly this is done, we're not going to really cover because that then gets very specific to JVM, the browser you use, whatever. So there's very complicated methods like how exactly this happens, but this is the general idea. How do you guys feel about this? Does it make sense in general? Any questions do you want to ask about how this works, how this looks, or confusions about it, because it is a fairly complicated topic, and most of you have not even taken a compiler course before. So
I want to note that JIT's also really useful. Like JVM is a virtual machine that uses JIT, but then like, who here has like a M1, M2 MacBook? Right. If you wanted to run x86 code efficiently, you could make a giant if-else tree to do all the Intel instructions and rewrite it. Or you could write a super efficient JIT, which is what industry does. And basically any like VMware like x86 you run on a like ARM chip will be using a JIT under the hood. Right. So like, if you want to, we'll talk about it in a later lecture, but like the world's best emulation systems are just all massive JITs, more or less.
anyone else have any questions?
So you said like executing that function a lot just from the bytecode would take a lot longer than the bytecode the interpreter for the bytecode talking to the JIT compiler and then getting the machine code for it?
Yeah, because this compilation you do once then. So you call this function 10,000 times, maybe you realize this function is being called a lot. This is relevant to my performance because it's being called so often and it's always slow in the interpreter. So it's just going to JIT compile it once and then save the actual assembly machine code to like some memory buffer. And then whenever the bytecode would call this function instead and like interpret the bytecode for it, instead it's just going to execute like an x86 call instruction to the beginning of this buffer, and it's going to start executing this, and then it's going to go back to the bytecode interpreter. It's kind of what you did with your the midterm stuff, the mprotect stuff, right, Stephen? The midterm had the mprotect stuff.
Yeah.
That's kind of how JITs work. So they call mprotect on some memory region to make it readable, writable, and executable for themselves. Then they write some code to it, and then they tell this code to just jump to this location. Basically exactly what you did in your project and your midterm as like an exploitation thing. These real projects, like your browser, for example, it does that too.
So it's not called on every section of the code, just sections that would be worth it based off of some calculation?
Yes. So it's going to depend on like your application. So if we're talking about, like Steve mentioned, emulators like QEMU and whatever, they're going to JIT compile everything because they can. But if you're talking about like the JVM or browsers or whatever, they're not going to do everything. Because especially when you're loading a website, there's like different performance you care about. One is like the performance as you're like using the website, and one is kind of like the startup cost. So if you were to take all of the JavaScript on the website and instantly JIT compile everything, your website would load very slow because like this compilation process takes a lot of time. So what you do is you initially just convert everything to bytecode because that's fast, and then you just start executing it. And then only the ones you care about, you invest the time to actually JIT compile it and make it even faster. Because otherwise, if you just compile everything, your website would take 5 seconds to load because compiling and doing all these optimizations takes time. But yeah, and then there's some applications like, for example, Pin or QEMU, they JIT compile everything. I'm going to talk more about how Pin does it later in a second.
Is WASM pre-compiled JIT?
Probably a bit of both. I don't know too much about it, but I think WASM. Do people know what WASM is? Yeah, it's basically an assembly that's meant to run on the web. Browsers by default have an interpreter for it, but they also have a JIT for it. And I think it operates for most browsers about the same way as for JavaScript, where you optimize it if you have to, and otherwise you're just going to interpret it. That's my basic understanding of it, but I've never looked too far into it. Yeah. Any other questions? Okay. So let's talk a bit about what Pin does. So we'll talk about how the JVM and JavaScript engines, they get bytecode and then they optimize that when they have to. With Pin, it doesn't really work that way. So to execute Pin, you just give it some binary. So you take some binary from your system, like /bin/ls, for example, you point Pin to it and you tell it to do its thing. It doesn't have bytecode, it doesn't have source code, it doesn't know anything about the program except the binary you give it. So what can Pin do in this case? So the first step it always has to do is pretty much to take the binary you give it and to kind of parse it out. So L files have a specific file format. We talked about it a little bit at the start of the lecture. So Pin can use that to, for example, find where the first instruction is that's being executed. It can find like the GOT, the PLT, all of these sections. Pin can find itself. Like it can just parse the static binary like that's on the system without having to run it, and it can just find these sections and information. So that's the first thing it does. It takes the ELF and like generates some internal mapping of it. Next, then to actually execute it, it's going to go to the start location. So let's say you parse your binary, and inside of the ELF header, there's like a field that says what the address is of the first instruction that's going to be executed. So let's say this is at 0x1000. Let's say this is the start location, so the beginning of your start function. So it's going to find this, and then once it starts actually wanting to run the program, it's going to look at this location. The 0x1000. And at this location, there's going to be some instruction. Let's say it's move EAX 0. So what it's going to do is you give it, when you're using pin, you give it like the binary you're trying to execute and the script you want to run on the binary. So then let's say your script basically says for every instruction, just print out the address. So we get here, pin sees this is the first instruction. It can't just execute the instruction or point RIP here and then just like have it execute. Because then it's just going to go from this instruction down to the next instruction and then down to the next instruction and so on. You don't want this. Because like if you just set PC equals this, it's just going to start executing there and pin lost all control. So what pin does instead is first of all, it's going to parse this instruction. So it's going to see, okay, this is a move EAX0 instruction. So it's going to take this. And then it's going to apply your path to it, like your path to it. So it's going to like allocate some other memory region using mprotect or something of that sort, or mmap that's like that's executable. And into this memory region, it's going to first then insert a call, maybe it's like call printf using %d and like the address you gave it, or like the address of this that it knows. And then it's going to copy the actual instruction over. And then since these occur in the same block, pin knows, okay, this has to execute after it, so I'm going to insert that in here as well. This has to execute after it, so I'm going to insert that in here as well. And after every single one, it's going to insert this call to print, and then it's going to copy this over. Does this make sense so far? So you have your instructions in a control flow graph block, and you know these instructions are always going to execute one after another. So what you do is just you go through all the instructions in one block that you know have to execute after one another, and then you just rewrite them to some memory buffer that's executable, where you include the instrumentation your user told them to do. So for example, like print the address out. So you can do another print, and then you insert the next instruction you copy over, and so on. And whenever there's like some address, like for example, if you're loading from memory, pin then needs to like convert that address like the memory space does itself, and so on. So there's like more it has to do in the background, but that's the general idea. Does it make sense how like a single block can translate for everyone? Okay, so then what happens if a block ends? So let's see. So you have like this control flow graph, and at this point in this graph, you have an if statement, and you check if v1 is equal to v2. You don't know what this the result of this comparison is going to be until you know what v1 and v2 are. Maybe v1 and v2 are like set using some like operations in here. So at the start of this block, before executing it, pin cannot know what the result of this operation is. So what do you think pin could do at this point? Does anyone want to provide an idea? So pin does not know what instruction is going to be executed after this block. So what can it do instead?
It can make a prediction.
It cannot. Unfortunately, no, because you don't want to predict in this case. Let's say you predict wrong, and then your program is going to be executing differently than it should. Because this is a dynamic technique where you don't want to like have stuff occur and then it's like if you do, let's say you make a prediction and say it's going to go there. Well, then you're going to start compiling code into here that actually goes there, and then your code is actually just going to jump there. There's like nothing you can do to fix that. So you can't just make a prediction. You need to actually know where it's going to go before you can tell it to go somewhere. Yeah.
Can you just hook both like we did with the move EAX?
So insert a hook at the beginning of both of these, you say?
Yeah.
So you just compile. Okay, that is almost there. The one issue with that is that you need to then compile both of those blocks entirely beforehand. So what you can do, so you need to like compile both these blocks, and at the beginning of both these blocks, you insert like something that like checks am I supposed, and then like returns back to the control back to pin. A much easier way is though kind of if you know that, let's say this is the if statement here, you're just gonna, before this if statement executes, or like at the if statement execution, you're just gonna insert some instruction here that just jump. That just returns control back to pin. So at this point, all of this code has executed, and then at this point, pin can know what the result of this is. So it's going to have all this code executing until the if statement, and then it's going, or even the if statement is going to have execute until it like knows the result, and then it's going to return to the engine. And at this point, it knows if either this is going to be executing or this is going to be executing. So what pin can do now is can grow this executable buffer, and the block that, let's say this block was picked by the execution, and that's just going to do the exact same thing again, and just in time compile this block. So you don't compile everything, you just compile one block at a time, and then you check what block's going to be called next by executing it, and then once you get to that point where you know what's going to be executed, you take that and you compile it into the cache. But yeah, your idea was very close, like almost what it does. Any questions on this? Okay. So one detail that we left out in this entire process is that there's a middle step between this here. So pin sees these instructions, and it's going to parse them out into an intermediate representation. So in every single block, it's going to parse into like some form of intermediate representation. What this does is that you can do a lot more fine-grained analysis. This is, for example, something like Frida does not do. What that pin and like Dynamorio and those tools, they do that. Valgrind does it too. So it lifts this code, it parses it all out, and lifts it into some form of intermediate representation. And then as the user of pin, you can not just insert instructions before or after instructions, or before and after like blocks and whatever. You can actually modify the instructions in this block itself. So pin is then going to give you an IR that says, let's say you tell it to hook every single block, and then you can, inside of your pin tool, you can say, in this block, print out all the instructions all the IR instructions that are in this block. So it's going to give them all to you. And then you can say, okay, for instruction 3, I want you to replace this instruction with a not. And you can do that very fine-grained. Or you can say, if you find an add instruction, replace it with a sub instruction. These are all things you can do with pin from this IR. So it has this API that operates on this IR. So as a user, your pin tool then gets executed right to you on this IR. And then you can modify what's in this IR, and then it's going to get compiled into this block. We're going to look at some examples of how this looks in a second. Is everyone still familiar with what I was referring to with IR, with some form of intermediate representation? Okay. Okay, let's move on to a little bit of an example that might be a bit prettier than the board drawings. So let's say we have this initial x86 program. We have some instructions. Let's say these are individual blocks here in this case. There isn't really any control flow between them, so they'd all be in one block, but let's just for argument's sake say that these are different blocks, and you're using your pin tool and you wrote some tool that says, for every block, do something. In our case, let's say we want to count how many blocks are being executed. So what we can do with this is we write our instrumentation routine that says after every instruction in a block, insert increment some counter. So you're going to allocate some counter and then like modify your program in a way where after every instruction it's going to add another instruction that just modifies your counter. So as I said earlier, pin goes one block at a time. So let's say this is the end of a block, it doesn't know what's going to be executed next. So it's going to take this, it's going to compile it into this. And that's all it's going to do, and then it's going to insert like some code at the end of it that returns control to pin after this block has been executed. So you modify this program, you can assume that this is on the IR in this case, and it's going to take this program and write it to the code cache. So this is then the final region that you allocated with executable permissions. And then you go to the second block, you do the exact same thing again. You have your instruction here, you modify it inside of your pin routine, and you actually emit that. One more time, go to the last block, and do the exact same thing again. And now you just JIT compiled your entire program. And you execute this. Let's go back to the slide. So you write this to the JIT cache, then pin jumps to it, executes it, and the control goes back to pin, moves on to the next block, compiles it, executes it, goes back to pin, and it keeps doing this for every single block. Does this make sense to people? The general pipeline and how pin works. Yeah.
So it doesn't compile the entire thing, then execute the entire thing. It compiles and executes one block at a
Yes,
time.
exactly. Every single block gets compiled once at a time and keeps going like that. If you're looking at the JVM and other stuff, they usually do it on a function basis. Pin can't do it on a function basis because pin doesn't know what the functions in the program are. So if you only have a binary and no source code, and there are no debug symbols, you can't with 100% certainty say this is where a function starts and this is where a function ends. The only thing a pin knows is this is the starting point, and then at this location, the block ends. So, and I don't know where it continues executing. So it needs to execute one block, check where it goes, and then compile the next block, and it does that for the entire program that it needs to execute. When you're dealing with JVM or browsers or whatever, they have the JavaScript source code or Java source code, so they know where the function starts and ends, so they can just compile the entire function at once, which is a bit more efficient because it can do better optimizations when it has the entire function than just a single block. But yeah. Any other questions? All right. Let's look at a first demo then. So we're going to do the exact same thing that we kind of did here, where we just counted instructions. Let's look at how that actually looks inside the pin tool. I can copy paste from this. All right. And this is not some tool I wrote myself. This is one of the examples that comes with pin. So once you have project 6 is released and you start doing it, you can git clone you're going to be told to install pin yourself, and inside of pin you're going to see this path there, source/tool/manual examples. And here are a bunch of examples that just come with pin that you can look at how that's pin comes with, and you can kind of look at the source code and see how they implemented some things and maybe use that to help yourself on your own thing. So there are, for example, multiple routines. Zoom in a bit. For example, there are a couple of different routines that handle some form of instruction counting, different ways of doing that. Looks like there is instruction trace that prints out all the instructions. Little malloc.c that might, I haven't looked at it, but that might, for example, be a hook to your malloc allocator and replace it with their own allocator and so on. So you can look at, when you're working on your project, maybe you're confused about how you can do something, you could always refer to some of these examples and see how they did it. So let's look at the instruction count example. This is pretty much the simplest example that comes with pin. It's, let's see. It's about 80 lines of code, very small, and most of it is kind of just boilerplate to get pin to run. So start from the main function. So we have the main function here. We start by just initializing pin. So this is kind of going to take your binary and start parsing it. That's all. It's also like does some setup for pin. This is kind of just a routine that comes with it. And whenever you write a pin tool, you're starting off by calling pin init. If this call fails for some reason, maybe you didn't provide a valid pin tool or whatever, it's going to call the usage function, which just prints out some usage instructions. Simple enough so far. Next is going to open some output file, or you don't have to do it, but for example, if you don't want to just write your output to standard out, you can then just tell it to like open some output file. And this is C++ code, not C, so if you aren't familiar with it, it's going to look a bit different, but I don't think you need to worry about it. You're not going to have to like use any advanced C++ concept. You can basically just write C and do some slight modifications to it to make it conform to C++. But yeah, so here we're going to be opening an output file. They parse command line arguments through some tool or library, whatever that's called knob. I've never used it outside of pin before, but it seems to work fairly easily, where you can just specify the outputs here, and if the outputs aren't correct, it's going to get all the arguments, and if they aren't correct, then it's going to print out the usage for you. So it's very easy to use. You can just look at the example, and yeah. So this is like parse the arguments and opens an output file for you, where you're going to emit the output to. And this is where the first interesting thing happens. So here you register a hook that hooks all instructions. And you add an instrument function that for every instruction, you're going to call this function. Instruction is one of the functions that you define yourself. So for every single, you're basically telling it that for every single instruction, call this function that I define here. Let's go back to it. And next, you're just going to register another instruction that basically, the add fini function, basically when pin is done executing the program, it's going to call this function. So this function is another one you define yourself, just call it fini here, or in this case, and this does usually some cleanup or like printing out your outputs, whatever. So this is pretty much all you have to do for like your registering your pin tool. You tell every instruction, you tell what to do when it's done, and you just tell it to run the program. So simple enough so far. So let's look at the instruction function. So for every single instruction, we now execute this. And what we're basically telling it is to insert a call to this user-defined function, do count. We're also telling it that we're not providing it any arguments, and we're giving it a flag that says execute this before the instruction executes. So you could also put I point after, and that will then execute it after the instruction executes. So for every single instruction, before the instruction executes, call do count, and then it's going to execute the instructions. So it's going to call do count, and all do count does, it increments I count. And I count is just an unsigned integer here that's defined globally. And then the other thing we registered, if you look back, is the add fini function where we registered fini. So if we look at fini, this sets some options for the output file, not even sure what that is. And then it's just going to write the count using the icount as C++ print syntax. This one is just a print to the file of like the instruction count we have. Any questions on this before we start running it? Okay. So let's copy the other line here. So if we look at the options of how we're running it, we're executing the pin binary. This one comes with pin when you install it. I do not believe that this is open source. So if we look back like a few directories here, we can see that there's like some executable. It's called pin. This is what ships with the application. So we're executing pin. Then we're specifying the tool we wrote. So we compiled the tool to a library, so .so file. And so we're telling pin to run it with this. And then we're providing the output file because the tool requested that. And then we're writing everything to instruction count 0.log. And we're going to execute the binary /bin/ls. So what we're doing is we're executing pin ls. We're going to run our pin tool on this to hook every single instruction. And the fini function is then going to write our output to this log file. So let's run it. It finished running. As you can see, it printed out the directory here. This is because the ls was actually executed here. So pin did not just do it statically, it executed the ls and hooked stuff while it was running. So we can now look at the instruction count, .log, and it printed out that while executing ls, it executed about 685,000 instructions. And we can run that against some different binary. Let's choose what we want to do. /bin/true, a very simple Linux binary that I believe just prints true, or like returns 0 for true or whatever. And once again wrote it to instruction count. And we can see that running true, which is a lot simpler than ls, only took about 167,000 instructions, which is still a lot, but that includes like all the initialization routines that come with like libc and all of that stuff. So yeah, we could run that against pretty much any program on your system, and it should just work and give you the amount of instructions that have been executed. Any questions on this? All right, let's look at another simple demo then. This time, a demo that does an address trace. So with this demo, let's just open it up real quick, it's probably easier. iTrace. Okay, let's go back to the bottom. Only 66 lines of code, also very simple. Once again, we're going to initialize pin, we're going to open up some trace file. We're going to tell it in this time, or once again, to insert every single instruction. So the instruction is using this ins prefix. If you want to insert every single function or block, you give it a different prefix. And you can look at the examples or pin documentation to figure out what exactly the APIs are. And we're going to once again tell every single instruction, we call the instruction function, and then at the end of the program, we call the fini function. Look at fini, it's once again just going to write the trace to a file, and then close the file. Oh, actually, this looks like it's just going to close the file, actually. It's not going to. Oh, yeah. So the fini function in this case isn't going to do any printing or whatever. It's just going to write an end of line to it or end of file to the file, and then just close the file. And then inside of the instruction function that we hook, so for every single instruction, we're now inserting a call that before the instruction, so I point before, we're going to call the print IP function. And in this case, we're going to give it as an argument the instruction pointer. So it's going to specify that using this and no other arguments. So looking at the print IP function here, it takes the instruction pointer as an argument, and then execution-wise, it just calls it an fprintf onto the trace, and it prints, like, it just writes to the file the IP as a pointer. Simple enough. Just once again execute it. Using ls again. This time we did not specify an output file. So what was the output file by default? Oh, just iTrace on it. Like we didn't specify through the command line, we specified it inside of the code. So we can cat this out, and we can see a bunch of addresses, and this is basically the full instruction trace for every single instruction that executed, just printed out an address. Kind of cool. And these are very simple paths. You can do a lot more complex things with this. You can modify the instructions. You can go and every single add instruction, you just replace it with a sub instruction, see what happens. Probably a lot of bad things. But you can do very interesting things with this. Okay. Any questions before we move on to taint analysis? So when you're actually doing your project, I would recommend that you, number one, you first install a pin, you play around with the default examples that are provided, make sure you compile all of them, run them, and just play around with them a bit. And then just look at the other examples, see how they did maybe some more complex things, how they maybe hooked a function and replaced a function call to one function to a function call to a different function. There are different hooks in there that do various things, and based on them you can kind of like get some strong reference in how you do things. And there are also a lot of, Pin has good public documentation that you can access. There are a good few blog posts on it that cover how to use it. Some colleges have lectures on how to use it and so on. And you can refer to all of them when you're working on your project. There are going to be a couple of resources linked with that come with it. Yeah. Okay, now let's talk about the next dynamic and pretty much the final dynamic instrumentation technique we're talking about for this class, and that being taint analysis. So with taint analysis, generally your main goal is to determine how data flows through the program. And this can be done statically using some form of data flow analysis where you operate onto the control flow graphs and determine how data travels from one location to the next. Or you can do it dynamically. The dynamic way is usually referred to as dynamic taint analysis. And this is usually done by marking some bytes in memory and tracking how they flow through program execution. So you might have like some form of memory region here, and you say that this region is interesting to me. So you might color all these bytes, mark them in some way. And whenever there's an instruction, let's say this memory is at 0x1000 to 0x1090. Let's say this is the region you care about. This could be some of your user input. You want to see where it travels. So you mark all this entire memory region. And whenever some operation operates on data from this memory, like for example, a move instruction that moves into racks from somewhere in this memory region. So if let's say 0x1020 and moves that into racks, you're going to see this instruction and you're going to mark that whatever's in racks is currently marked from your memory. And you're going to keep this chain alive kind of, where you then see, okay, if something is done using racks, let's say racks are added to like some RDI and then stored to some other memory location, all of that you're also going to mark. And using that, you can know where exactly your data is traveling through the program during execution. So if you want to like compare it to like a real world example, maybe you have some river and it goes underground somewhere, you don't know where it's going, which kind of like you compare to like executing a binary, you don't know what's actually happening inside of it. And what you can do is you dump a bunch of color into the river, which you probably shouldn't do, but you could. And then you're going to just look at where this colored water flows out. So you're going to look at all the seas and rivers surrounding your one river, and you're going to see where the water resurfaces this colored water. And that's kind of what you do with taint analysis just for programs. So since this is a dynamic technique, and you need to hook all these instructions, this is usually done onto like some other framework like PIN. So let's erase the board again. Should be enough space. So let's talk about how that's done in practice. So on 32-bit, we're just going to talk from like a 32-bit program perspective, because for a 64-bit, the algorithms in the background get a bit more complicated. Let's say you have a 32-bit program. Your memory space is fairly small for modern standards. So what you do is you can just allocate a giant bit map. So for every single byte of memory, you can have a bit in this map that says that is either set to 0 or to 1. And if it's set to 1, this bit is marked. If it's set to 0, this bit is not marked. So for your entire address space, you map into this bitmap. Since you're doing bits to bytes, this memory region would have to be about 2 to the power of 29 bytes large, I believe. Okay. Potentially. I'm not sure. Math's hard. According to my notes, it's about 512 megabytes, which it's a good bit of RAM, but for a modern computer, it can handle it. So you allocate this massive bitmap, pretty much. And then let's say you find some function that gets user input. Let's say you have like some fgets call. You don't have a buffer overflow on the fgets, but like you have some buffer, and then it like reads in some input from you. And you want to know what your input actually touches. Does your input maybe reach some call to system? This is, for example, a very common vuln if you're looking at embedded devices that use a call like system to execute something. And you might use taint analysis to see if anything that you write to this buffer is getting parsed out and whatever, and will eventually be like an argument to a system call, for example. That could instantly be a vulnerability. Or maybe you want to see if something in there is being passed to a string compare. And that you could, for example, use to check if you can get, to modify your input to get further into the program. So you could, for example, combine this with fuzzing to make the fuzzer smarter and pass these string compares. Attempts have been made in that. In general, it's kind of too slow to be super relevant for fuzzing, but it is a possibility that people have explored. So, yeah, so this is the general region. So there are some considerations to make with this. In theory, it's simple enough. You just have this massive region. Let's say this is your fgets call. I didn't finish my example. And let's say this buffer is allocated at like some address. Let's say this region in your bitmap. And then you mark everything in this region to a 1. So everything in this region is set in your bitmap. And then whenever there's an operation in memory that uses some data from this bitmap and passes on to some other region of memory or some register, you can also mark that thing that operated on it also with a 1. And through that, while your program is executing, over time, you're going to find a bunch of other memory locations that interacted with your initial inputs that are now tainted by it. And that's the general idea of dynamic taint analysis. Questions on this? Yes?
It's somewhat similar to address sanitization.
Not. I mean, it is in terms that it's both dynamic and with both you're kind of modifying your program. I'm not sure. I don't think address sanitizer actually does taint analysis for it, but you could, in theory, also do address sanitizer using dynamic taint analysis, which is kind of a more expensive technique. Where with the address sanitizer you can kind of do things a bit simpler and still make it work because you have source code oftentimes and stuff. But yeah, you could use this for address sanitization as well to a degree. Any other questions? Yeah.
Can I just tell you like when like the data was hit, or just like that the data was hit?
So it kind of depends. This is kind of where your implementation of it comes in. Because if you look at this is a massive memory region you need to allocate. And let's say, in theory, if you had infinite memory, you could record not just a bit in the bitmap, but also at which instruction pointer this was done. But now you suddenly, every instruction pointer is up to 8 bytes long, and now instead of 1 bit per byte, you need to store 8 bytes per bit, or per byte. So if you have 64 times the amount of memory as this is, I think I said it's about half a gig. So if you have 32 gigs of RAM, let's say double it, because your program also needs some RAM to execute and stuff like that. But if you have a server with 64 gigs of RAM, you could do a full recording of everything. Or you could optimize it a bit and just sometimes when it's hit, you record the IP, or you only record part of the IP and like do the mappings yourself afterwards. So if you wanted to, you could. With taint analysis, it just very quickly gets very memory heavy, so you need to be careful about what exactly you track. But yeah, it's possible. Okay. So there are 3 main steps when you do this type of analysis. So first, you need to define the taint sources. So in this example, it was just this buffer that was an argument to fgets, because you know that your user input gets written to this buffer. So you define this as your source. So you could, for example, say that for every single read syscall, you want to hook that. Maybe for every single memory operation, like whenever it reads data from the network, you want to hook that as like one of your taint sources. So you define your taint source first of all. Then you define your sinks. These are locations where you're curious if they are affected by your taint sources. So this could be a call to system, a call to string compare, a call to memcopy. It could be a call to just a function that you think might have a bug and you want to see if your input can reach this function. You basically define anything you want for it. And these are basically, you want to see if some data can get from the source to the sink. And then you need to define some policy that defines how the input is propagated. So every instruction that handles the taint data in one way or another, be it a move, be it a XOR, an add, a call with an argument of the taint, whatever, all of these need to be instrumented and propagate the taint in some way. So if the input instruction then is tainted that goes into it and it writes to some output memory value or register, this output needs to be tainted now too. And using this, it can basically be propagated from the very beginning of the program to the very end. So let's talk about some design considerations. First of all, the taint granularity. So with this, the main concern is kind of how fine-grained do we want to make our tracking. So in this example, I said you can allocate 1 bit for every byte of memory. But this then means you can also only say if this byte is tainted. you can say that maybe the lower 4 bits of this byte are tainted, but the upper 4 bits are not tainted. So you could make it a lot more fine-grained. But this then, you would also, if you want to do it at a bit level, you'd also need 8 times the memory space, because you now need to allocate 1 bit for every bit of program memory. Alternatively, you could go the other way. Let's say maybe you don't have that much memory. So instead, you could track taint on a word level. So maybe for every 4 bytes, you allocate 1 bit in the bitmap. So whenever 4 bytes are tainted, if they interact with some other bytes, if 1 byte out of those 4 bytes interacts with one other byte of a different set of 4 bytes, these entire 4 bytes are now also tainted. This now only uses 1/4 of the memory that this map used, because now you're using 1 bit for every 4 bytes. So with the granularity, you can kind of go more fine-grained and use more memory, or less fine-grained and use less memory. And how you do this is generally going to depend on use case, but a good general average is just having 1 bit per 1 byte, and that's a default that most taint analysis engines use. And then there's taint colors. So you can, let's say you have several taint sources. So you might have this fgets call here. Maybe you have another fgets call in some other function. And then maybe you have a read call that reads data from a network and or a receive. So you have 3 taint sources. And you could mark them all using this 1 bitmap and then just propagate the taint that way. But then once it actually gets to this source, you don't know if, since you only have this bitmap, you don't know if the source came from this fgets, or from the receive. So this is where taint colors comes in, where you kind of color your different sources using different bits. So this, once again, just depends on your memory pressure, how much memory you have available, and what your goals are. So if you wanted to track 8 colors at once, you might allocate, on a byte level, byte granularity, you might allocate 8 bits in your bitmap, say this 8 for every byte, and then you could track 8 input sources by just in the memory setting the bit according to this input. This is all you can go more fine-grained the more memory you have available with this. And then there's taint policies, which is almost the most relevant one. Actually, the other ones are also very relevant. This one is also very relevant. And with this, you kind of describe how taint is propagated. So, for example, let's say you have a XOR operation using 2 registers, let's say RAX and RBX. Now, one thing you could do, let's assume that RBX is a taint source. So RBX is tainted. What you could do is say RAX interacting with RBX, the entirety of RAX is now tainted. You could also instead maybe look at what in RAX was actually modified, and only this is tainted. You could set up a policy that maybe if it's a XOR instruction, it doesn't consider it tainted at all, and only considers it tainted if some part of RBX is moved over into RAX to remove instruction. Or maybe an add instruction that only modifies the lower 8 bits. Are you going to consider the entirety of RAX tainted now, or only the lower 8 bits? So there's a lot of considerations with your taint policy, where when you're hooking every single instruction and determining if it was tainted or not, that you need to put into that to determine how you want to design that. Any questions on taint analysis? This is not something you're going to be doing in your project, mostly because we kind of ran out of time and out of projects, but it's a very interesting technique that don't start going to the space where you start needing servers to actually do it, because running it on your laptop could very easily run out of memory, especially when you have a 64-bit memory space where you can't just allocate a giant bitmap to cover this entire memory space. So there are a lot of considerations that go into it, but it's a very interesting technique that if you're interested in learning more about it and how to use it, there's a book called Practical Binary Analysis that covers it in detail and how to combine a dynamic taint analysis library with PIN to do this type of analysis on a program where you can define some input, define a source, define a sink, and see how the data travels from one end to the other. You can define some taint policies and so on, and this book covers some examples of that. We're not going to be doing that in a practical sense, but I just kind of want to introduce the theory to people because it's very interesting. Also going to, actually no, it's not going to happen tonight. But yeah, any questions on this? or on like any other form of dynamic binary analysis. Next week we're going to start with static dynamic analysis. Static analysis. Or lecture after that we will do static dynamic analysis, kind of like a combination of both, but that's not like next lecture. That also you'd probably say hybrid analysis, not static dynamic, but yeah. If there are no questions, then that's it for today.